Our first speaker in this session is Toby Lam, and Toby's from the University of Oxford. He'll be speaking about symmetries of differential equations. Go ahead, Toby.
Right, so I'm going to start. So first of all, what are symmetries of differential equations? And there's this fancy definition. It transforms a solution to a differential equation to another solution of differential equation. And so basically why anyone would care about this is that differential equations, why do we care about differential equations in the first place? It's because they're trying to model, right, some sort of physical, chemical, or biological phenomena. Symmetries map solutions to other solutions. And so symmetries of differential equations try to relate different physical, chemical, or biological phenomena that are kind of similar to each other. So I can start off with a very simple example. Say I'm trying to model a ball falling to the ground from rest. There's going to be some differential equation governing it. And what are its symmetries going to be? Well, its symmetries are going to be, say, time translation, right? So for example, if I drop this cap, if I drop this cap right now versus dropping this cap. Okay, wait, what's going on? Okay, versus dropping this cap like 1 second later, it's going to look pretty much exactly the same. And so there's going to be some sort of time translation in the symmetry. There's also a position translation. So if I drop this cap in London versus dropping this cap in Paris, they're basically the same sort of phenomena, except, I have to translate all the positions as well. So that's kind of, why we would care about symmetries of differential equations. They describe how dropping a pen in London versus dropping a pen in Paris, how are they related to each other? It turns out that they're very much related to each other. So, classically, there's going to be Northrup's theorem. It tells us that symmetries give us invariance, and in turn, they make equations integrable. Today, I'm going to deviate slightly away from that and, not focus too much on, integrable systems or systems where there is a Lagrangian, but more so on just general ordinary differential equations. And basically, how are solutions going to be related to each other? So there's going to be mainly three ways why we care about this. We can generate new solutions from old ones. We can understand, why these relationships exist in the first place, which tells us a lot about the physical phenomena at hand. And this is especially relevant for PDEs because, PDEs, the solutions to PDEs are often very complicated. And so symmetries there would really help us understand them more. So first off, I'm going to start with a very simple example, which is to think about straight lines. So to model straight lines, we can say that, well, what are straight lines? The second derivative is 0. And so the solutions are going to be straight lines. That's going to be determined by its slope, that's v, and it's also going to be determined by the initial constant. So that's like S0. So most of the symmetries are going to be exactly what you expect. So for example, there's going to be like horizontal translations, there's going to be scaling symmetries, and there's also going to be like shearing symmetries. So for example, I can show you some of these symmetries. So for example, in here, I have this left plane over here, I have this right plane over here. Right now, I'm going to model just, horizontal translations. So what we would do is that it's going to map like every straight line on the left, is kind of horizontally translated over time. And as you can see, this sort of symmetry, this sort of translation, no matter what kind of parameter you throw at it, no matter how much you horizontally translate, every straight line is still going to be a straight line. Something more complicated, let me set this up right first. Something more complicated would be, say, a shearing map. And shear, as we know, is still going to preserve straight lines. So now I want to kind of, make this notion of a symmetry more precise. So first of all, again, we see that we have to construct this sort of map from the real plane to the real plane. And so we're going to have like the left plane and the right plane. The left plane is going to be the original plane, and the right plane is going to be the new plane. And we have this phi, so this is some sort of function that depends on the parameter epsilon that maps the left plane to the right plane. So as we have seen earlier, in the case of horizontal translation, we can kind of imagine that there's like a lot of tiny water particles on the left ST plane, and this map tells it to move it rightwards, right? We're moving each individual water particle to the right, and we see that we're just moving every particle from the left to the right. So this kind of represents horizontal translation by epsilon. So that's all well and good. So what do I mean by symmetry? Well, first of all, let's say I have some function S of t on the left plane, and then I focus on how this symmetry maps each of the individual points of the plot of S of t. It moves it to the right. Now we want to write what's on the right as a function, S hat of t hat. Now, obviously, if the symmetry is really bad looking, we might not be able to write the right-hand side as a function as a well-defined function. But for the most part, we can do that, right? And we say that this phi of epsilon is a symmetry if it maps solutions to solutions. So if the left-hand side, we have a solution to this differential equation, in the case, if we have a straight line on the left, then the symmetry always takes straight lines to straight lines, then this is going to be a symmetry. So this is just a more complicated version of saying that a symmetry of a straight line is a symmetry if it takes straight lines to straight lines. So that's all well and good. You might think about, what's so interesting about this. So, well, first of all, let me just try to get some vocabulary in hand. So from now on, I might refer to this as some sort of transformation, because this really is a transformation from the plane to the plane. I might refer to it as a symmetry as well. And in fact, I might also say that it's a Lie group element. So because this is some sort of symmetries from groups. And in this case, we're kind of interested in continuous groups, and we call continuous groups Lie groups. We can also visualize these transformations using a velocity vector field, right? So back to this case, you can think of these water particles as moving under a uniform rightward velocity vector field. And so we represent it as a vector field. And so this is kind of like a velocity vector field. We integrate this, and we get the actual group element. And so this is kind of like what we call the Lie algebra in pure mathematics. So this is all very well expected. What's interesting about it, it turns out that there's actually two nonlinear transformations. So when you just look at these transformations, they don't look like they preserve straight lines, right? Straight lines should be linear. Why would there be any nonlinear transformations behind symmetries of straight lines? So let's actually just see this in action. So once again, we have the left plane, the right plane. If we play out these nonlinear symmetries, what we get is some sort of panning motion. So we can kind of see that we're kind of panning, we're kind of like tilting the camera, so that straight lines are still straight lines. And we can see that every straight line here, it's still going to be disturbed. So this is some sort of like nonlinear transformation that preserves straight lines. This might remind you of something, which is really panning a camera, and we can see this with a video game, right? So let's say here I have a 3D I have a character that's kind of moving in the ground. We're kind of looking downwards from the sky, and if we pan the camera, we see that every straight line is still a straight line. This is exactly what we've done. This is exactly what we've seen here. So somehow, what it's saying is that to consider all the symmetries of straight lines, we actually need to go to the 3D space. We need to go to the projective space. And so that's just, every camera motion that I'm doing is preserving straight lines. And this panning motion is exactly the nonlinear transformation that we've seen just before. So it's really rather interesting that we get something extrinsic. Previously we were just considering the real plane. Now we actually have to think about three-dimensional matrices. We have to think about projective linear transformations. And we can actually deduce this extrinsic sort of transformation just from thinking about the real plane. When we're deducing these sort of symmetries, we never considered that, we might be living in a three-dimensional space, right? All of these sort of calculations are done in two-dimensional only. So now let's look into some more non-trivial examples. Let's look into some PDEs. So here is Laplace's equation. So this is a very famous partial differential equations. What its symmetries going to be like? So some undergrads here may know, Laplace equation. How do we usually solve it? We usually do some sort of complex analysis. Why is complex analysis relevant here? That's because there's going to be some conformal maps. So we know that angle preserving maps preserves solutions to Laplace's equation. And we also know that orientation and angle preserving maps are exactly complex differentiable maps. And as such, the symmetries, in terms of the vector fields, are going to come from the derivatives of complex differentiable functions. And so we would expect some sort of Cauchy-Riemann integration, Cauchy-Riemann relations in terms of the complex analysis kind of gradually coming in to play. And so this theory of symmetries of differential equations doesn't really tell us anything new about Laplace's equation, right? You need complex analysis to really understand what's going on here. And I would want to make a comment that Laplace's equation is called an elliptic equation precisely because circles are ellipses. So that's kind of why, and circles live inside the Laplace equation because conformal maps preserve circles. So it's actually really aptly named. Why is Laplace's equation called an elliptic equation? It's because there's going to be circles involved in symmetries. So now we can move on to like some wave equation. So that's like a hyperbolic equation. And I'm going to go through like all these symmetries one by one. So first off, there's going to be V1 and V2. This is just the position and time translation that we've seen earlier. So that's nothing special. We can go to the D, which is this dilation. So all I'm saying here is that I'm just increasing the time frame and position frame equally, right? So instead of like considering 1 meter in 1 second, I consider 10 meters in 10 seconds. So that's not really a physically interesting symmetry. V3, I'm just expanding the amplitude of the wave. That's also not very interesting. The alpha, what I'm saying here is that if alpha was a solution to the wave equation, I can add it on to any existing solution. So this is I'm just saying the principle of superposition. What's far more interesting is perhaps this hyperbolic rotation and these inversions here. So I'm going to focus on the hyperbolic rotation. So if you have done some special relativity, you actually would see hyperbolic trigonometric function in special relativity, right? In like Minkowski space, whatever. And this is actually kind of like a good reason to think about why there even is hyperbolic trigonometry in relativity. It's kind of because hyperbolics are kind of forming a symmetry of this differential equation. In fact, we can compare this to the Laplace equation. In the Laplace equation, rotations are a symmetry, right? Because rotation is a complex differential map. And in the case of a rotation, would replace this hyperbolic trigonometry with just normal cosines and sines. So let's see this again in a real example. Here's like the wave equation. And now I want to apply, so this is some solution to the wave equation. X is position, Y is time, Z is amplitude. If we apply this hyperbolic rotation, we see that we're kind of actually decreasing the wavelength and also increasing the frequency at the same time. So the velocity is kind of preserved under this symmetry, which is to be expected. And we're just kind of decreasing the frequency and decreasing the wavelength at the same time. So that's kind of how the hyperbolic rotation is acting on it. There's also this fancy inversion here, which is kind of a bit too complicated to explain here, but I might just show you some animation. So here, for example, it's normal wave solution. As I apply this inversion, we're kind of like collapsing this wave, where we're kind of introducing some sort of instability in this wave equation that kind of makes it blow up. So this kind of appears, in normal fluid dynamics when you're studying like water waves or something like that, where the waves kind of like blowing up as you go. So finally, I want to talk about the heat equation. So once again, there's some very simple symmetries here. So for example, there's position translation. There's also time translation in V1 and V2. V3, what I'm saying is that I'm just kind of raising the temperature, by a factor of 2. Then, for example, if I raise the temperature by a factor of 2, it is going to stay raised by a factor of 2, no matter what. In V4, there's this interesting symmetry where we're kind of scaling the position and the time scale differently. So if I scaled up position by 2, then I actually have to scale up time by 4. And this is exactly why heat equation is called the parabolic equation, right? For example, for this one-dimensional heat equation, we have this solution minus x squared minus dt. If I doubled x, then I have to quadruple t. And this is exactly why heat equation is called the parabolic equation, because there's a parabolic relationship between the time scale and the position scale. Once again, the rest of the symmetries are more interesting. There's going to be, again, a principle of superposition here. There's going to be this sort of Galilean boost in V5. So we see that we're kind of changing the position by Galilean boost, right? If you forget about the heat term here, you can see that position is going to be raised by some sort of constant velocity times the time scale. And let's see this once again in action. So for example, here is like the fundamental solution of the heat equation. X is the position, Y is time, K is like the parameter for the fundamental solution. So these are just various solutions to the various fundamental solutions to the heat equation. If we apply the Galilean boost, we can kind of see that the peak of this heat wave is kind of moving with a constant velocity. So I'm kind of perturbing the initial configuration just the right amount that the peak of the heat equation, the peak of the heat, is kind of moving with this constant velocity as well. Finally, there's this very weird, very annoyingly looking V6 here. But once again, this actually looks really similar to the nonlinear transformations of straight lines that we were just seeing, right? We have this x over 1 minus 4 epsilon t, t over 1 minus 4 epsilon t, but this is exactly what we've seen here before. So now, in fact, it turns out that V6 actually transforms constant solutions into fundamental solutions. So in here, I have the fundamental solution right here. So this is like the fundamental, this is like the constant solution to the heat equation. As I apply the symmetry, kind of becomes the fundamental solution. Fine. And so that's it. So finally, the takeaways here, I would say that the symmetries are very powerful, right? They let us understand the model very clearly, and I think the more you use them, the more you spot it. And I think perhaps in a more advanced sense, as undergraduates, we learn a lot of these wave equations, heat equations, but in actual research, we actually need to find out these equations. At that point, it's no longer just about solving differential equations that we learned. It's not just about solving differential equations using Fourier analysis or numerical analysis. We actually need to construct these differential equations out of thin air. And when we're doing that, symmetries become very useful, right? Symmetries tell us something physical. And so, for example, if something is conserved that we're not expecting it to be conserved, then it's actually the differential equation that is problematic. Right? If you think back about something very simple like this model of a ball falling to the ground, as we know, in reality, gravity is dependent on position. Right? If you go higher up on the Earth, the gravitational constant is no longer the same as we experience it on Earth, and as such, this position translation symmetry is wrong. And so that means that the model is wrong. It means that this equation is also wrong. We actually needed to account for the height of the ball as well. So that's going to be the end of my presentation. Here's 2 books that I'm kind of referencing here. I also have a blog where I write about maths like this, and questions away.
Thank you very much, Toby. Yeah, we have time for a question. I believe there's one from Emiko in the chat. Why is V5 called the Galilean boost?
Yeah, so I hope that I was able to explain that slightly before. It's really just because of this. So forget about the U term. Just think about the x and the time. Whenever we add some sort of velocity to the position, we call this a Galilean boost. So we can actually kind of maybe look it up. Like we see that when we transform position by some sort of constant times time, this is called like a Galilean boost physics.
Okay, cool. Thanks. So I just have a comment before we move on to Yael. So Yael, can you get your presentation ready while we finish off with Toby? So yeah, just I really like how you kind of related back to the real world and how you motivated your talk. Yeah, thank you. I think it's really important to kind of show where differential equations come from and why symmetries in this case are important. Yeah. So yeah, thank you.
Great. Thanks.